Howdy. This video is on different types of equilibrium constants and solubility and KSP. There are many different types of equilibrium constants, so we should be able to recognize them. Solubility is one of the most common types of equilibrium reactions. Solubility is important in environmental chemistry and geochemistry. It determines what ionic species are present in lakes and rivers. It's also important in pharmaceutical chemistry, for example, how drugs dissolve. After watching this video, you should be able to write down the chemical reactions that correspond to the different types of equilibrium constants. You should be able to identify the type of equilibrium given the reaction. You should be able to identify the chemical formula of an ionic compound given its name. You should be able to identify the solubility as an equilibrium process. You should be able to identify the differences between solubility and solubility product constant. The solubility product constant is just an equilibrium constant. Given the KSP, you should be able to calculate the solubility, and given the solubility, you should be able to calculate the KSP. And so some equilibrium constants have subscripts which indicate a specific type of reaction. And so if you have no subscript, that just means equilibrium constant in terms of activities. The C indicates in terms of concentrations. Kw is the autoionization of water. Ka is acid dissociation of water. Kb is base dissociation of water. Acid dissociation of an acid, base dissociation of a base, obviously. KSP is a solubility product, and so that would be ionic solid dissolving, and Kf would be the formation constant. And so for autoionization of water, Kw, you have water going to hydrogen ions and hydroxide ions. If we write down the equilibrium expression, we have products over reactants. Pure solids, pure liquids do not appear. And so we have just Kw is equal to hydrogen ion concentration times hydroxide ion concentration. Autoionization means that water is breaking apart. And so that should hopefully help you remember that Kw corresponds to water breaking apart into hydrogen ions and hydroxide ions. And again, please remember pure solids, pure liquids do not appear in equilibrium expressions. You should also remember if we flip a reaction, so if we write the reaction as product, products as reactants, we take the inverse to get the new equilibrium constant. Ka corresponds to acid dissociation. So acid dissociation means that the acid breaks up into ions. And so again, we have products over reactants. And so this is our equilibrium expression. For acid dissociation, we're always going to have a hydrogen ion or hydronium ion as a product. And so we can write nitric acid forming hydrogen ions and nitrate ions. Sometimes we can also add water on this side and gives us hydronium ion and plus nitrate ion. What we'll see later is that the hydrogen ion and hydronium ion are actually the same thing. They just both represent hydrogen ion in water. Now again, if we take the products, write them as reactants, reactants as products, we take the inverse of the equilibrium constant to get the equilibrium constant of the new reaction. Kb is the base dissociation constant, and so the base breaking apart. And so again, products over reactants, coefficients become exponents, pure solids, pure liquids do not appear. For a Kb, we're always going to have hydroxide ion as a product. Now, base dissociation means that, base is breaking up in ions, and it's more appropriate if you're looking at a strong base. So like if you have sodium hydroxide, it breaks apart into sodium ions and hydroxide ions. Ammonia is a weak base, and so actually it reacts with water, forming the hydroxide ions. And so again, in general, base dissociation means that the base, that should be base, is breaking up into ions. And so we can write it this way. Or again, for weak bases, they react with water, forming the hydroxide ion and the other ion. The hydroxide for the weak bases actually comes from the water molecule. And again, if we take the products, write them as reactants, reactants as products, we take the inverse to get the new equilibrium constant. Solubility product KSP is just an equilibrium constant for an ionic solid going to aqueous ions. And so if we write down the expression, we're going to have products over reactants. Pure solids, pure liquids do not appear. And so it's a little confusing. We write down the equilibrium expression, and there is no products, right? Because the product is a solid. Now, if we take the products, reactants, reactants, products, again, Ekman constant is 1 over the KSP. So if you flip a reaction, you take the inverse of the Ekman constant to get the value for the new Ekman constant. And so here we have barium sulfate. And so, again, products or reactants, coefficients, organic solids, pure solids, pure liquids do not appear. Iron chloride, same thing. And again, please remember the coefficients become the exponents. So for the iron chloride, you have the iron concentration, the chloride ion concentration to the power of 3. Pure solids, pure liquids do not appear. Now we can determine the formula of ionic compounds by making sure that the net charge is 0. And so it's a little confusing. Ionic compounds' net charge is 0. They have no net charge, even though they're composed of charged species. And so you have to have as much negative charge as you have positive charge, so the combination is 0. And so for iron chloride, we have a +3 iron ion. We need 3 chloride ions to give us that charge neutral. And so that tells us that the formula should be FeCl3. For magnesium phosphate, magnesium is a +2. It's an alkaline earth. The phosphate, it's on our list of polyatomic ions to memorize. It's a -3. And so we need 3 magnesium ions for every 2 phosphate ions to get something that is charge neutral. And so you should remember the common charges of the common ions. So the alkali metals are +1s, alkaline earths +2, halogens -1, chalcogens -2, aluminum is a +3. And again, that will help us determine the formula for ionic compounds. You should also remember your list of polyatomic ions. And so we'll use this throughout the semester. You need to know the formula as well as the charge. And so the degree ionic solid dissolves in water is described by the KSP. It is the Ekman constant. And so for ionic solids that completely dissolve, KSP is very, very large. So if you think about table sodium chloride, you can dissolve a lot of sodium chloride in water, and so it has a very large KSP. There's also ionic solids that only slightly dissolve, and so they would have a very small KSP. And so again, sodium chloride, a lot of it dissolves, so its KSP is much greater than 1. If we drew the diagram where we had the free energy versus the reaction quotient, we'd see that we have product favored. Now, silver chloride, a very small fraction actually dissolves. Its KSP is 1.77 times 10 to the minus 10th. And so if we were to draw this diagram, we draw it something like this. Only a little bit of what would actually dissolve.
When a small amount of sodium chloride is added to 100 grams of water, it dissolves. If we add more and more salt, eventually no more can dissolve in this amount of water. The quantity of salt dissolved in this solution, about 35 grams at room temperature, is a measure of sodium chloride's solubility in water.
So solubility is the maximum amount of something that will dissolve in a set amount of solvent. Solubility product constant is the Ekman constant for an ionic solid dissolving. So please make sure you understand the difference between the two. And so initially, all of the solid dissolves. The solution is referred to as being unsaturated because we haven't reached the limit. And there is no precipitate, no solid. And so whenever the sodium ion concentration times the chloride ion concentration is less than the KSP, the system is not equilibrium. There is no solid, no precipitate. When a solution has the capacity to dissolve more, again, it's referred to as unsaturated. If we keep on adding salt, the solid, eventually as much as can dissolve has been added, then we refer to the solution as saturated. And so in this case, when the sodium ion concentration times chloride ion concentration equals KSP, we'd call the solution saturated. Now, if more solid is added, no more will actually dissolve. So we can't actually go past the KSP. So once a solution is saturated, no more solid will dissolve. Whenever there is a precipitate, precipitate's just a solid, it means that the sodium ion concentration times chloride ion concentration equals KSP. And so if we think about in terms of this graph, say this is for sodium chloride dissolving, initially we're starting with pure water. As we have the sodium chloride, it's dissolving. Eventually, when we get here, the most stable configuration, no more sodium chloride will dissolve. The sodium ion concentration times chloride ion concentration is a constant. Now, you could be asked a question of, given the KSP of something, what is the solubility? This is just an equilibrium problem. And you have to know the difference between KSP, which is the equilibrium constant, and solubility, which is the maximum amount of stuff that will dissolve in a given amount of solvent. And so when we're doing a solubility problem, we'll use this type of table. So we have our reaction, and then we have initial change equilibrium. Now, X is in units of moles or moles per liter. And so you can imagine that when X dissolves, so that's why it's minus, you'll get plus X for the bismuth, plus 3X for the iodine, because each time one of these dissolves, you'll get one of those and one of those. Now also we're assuming that we're starting with 0 bismuth ions and iodide ions in solution. Now for change, typically reactants will lose concentrations and products will gain, and so that's why I have a negative for the reactants and positive for the products. The coefficient in front goes in front of the X, so we're starting with coefficient of 3 in front of the iodine. That actually comes down to be in front of the X. The values of the equilibrium are equal to the initial plus the change. So initially we had no bismuth ions or iodide ions. And then when X dissolves, we'll get X of that and 3X of that. 0 plus X gives us X. 0 plus 3X gives us 3X. Usually we don't worry about keeping track of the solid because, remember, solids are not present in equilibrium expressions. And so we can write down an equilibrium expression for this reaction. Products over reactants. Pure solids, pure liquids are not listed. And coefficients become exponents. Now what we can do is we can plug in what was for at equilibrium. And so for the bismuth ion, we have X. So X goes there. For the iodide ion, we have 3X. So that becomes the iodine concentration. Now notice we have 3X and it gets cubed. Okay? So based on the ratio, when one of these dissolves, you get one of those and 3 of those. That's how we got the 3X. Now for the equilibrium expression, we have products over reactants, coefficients, peak exponents. That's how we got that 3. And so 3 cubed gives us 27. And so that's how we get 27x to the 4th. And so a little confusing, but notice the 3 comes here and the 3 goes there. And so we have KSP equals 27x to the 4th. We'll see later that there's basically 4 relationships between KSP and X. X is defined as our solubility. It's how much actually dissolved. And so we're given the KSP was 7.71 times 10 minus 19th. That's here. And so that equals 27x to the 4th. Divide both sides by 27. Take the 4th root. And we see that 1.3 times 10 minus 5 is equal to X. And so that means 1.3 times 10 minus 5 moles of bismuth iodide will dissolve in 1 liter of water. Now we can also look at the equilibrium concentrations. So at equilibrium, the concentration of the bismuth ion should be 1.3 times 10 to the minus 5. The concentration of the iodide ion should be 3x, which would be 3.9 times 10 minus 5. Again, please make sure you understand the difference between solubility and solubility product constant. Solubility is the maximum amount of stuff that will dissolve. KSP is the equilibrium constant. And again, please make sure you know these different equilibriums. The subscript indicates typically a specific type of reaction, and so you should be able to recognize different reactions, different types of equilibrium. I hope that helps.